Okay, so I'll start with A. So there's number 2. 2A asks for what is the theoretical flow time for an auto insurance application. So again, the flow time is the time it takes for the application to go from the beginning to the end of the entire process, assuming there's no wait time. So the first one is very easy. The process just has a single step. So therefore, it's just 20 minutes. For B, it's more complicated because we have 2 parallel steps that they can go through. So for B, remember that the bottleneck is the portion of the production chain that produces the least and limits how much the whole production process is able to produce. So produces the least. Okay, so when we look at steps when we look at, there's 2 paths here. There's the first path is A1 to A2 to A4, and the second one is A1 to A3 to A4. So that's this one here and this one here. So when we add up the theoretical flow time for A1, we have 15 here, plus 25 for Alex, plus the 20 for Richard, and this gives us 60 minutes. When we add up the second process, we have a process line. We have 15 plus 15 and then plus 20. So this is 50 minutes. Okay, so remember that the bottleneck is the one that produces the least and it limits the whole capacity of the entire process. So when you compare these, because 60 is bigger than 50, so the first path becomes because 60 is bigger than 50, this path takes the longer time. So when this one finishes, we still have to wait for this path to be completed before we can go to the next step. So because 60 is bigger than 50, the theoretical flow time of the homeowner's insurance applications is 60 minutes. So this one is the critical path. Yes. No, there's no difference. So C, what is the capacity of home auto insurance in applications per hour given its current product mix? So the trick here is the 60% homeowners insurance and the 40% auto insurance. So we have our resources are the staff. So we have Tom, Alex, Tina, and Richard. And then we have unit load and unit capacity. Okay. So how do you find the unit load of Tom? So we need to know that only 60% of the homeowner's insurance goes through the thought process here. Okay, and we assume that theoretical flow time means that there's no wait time. So what we need to do is, so unit load is 60% times whatever is given here for Tom, 15. So this is equal to 9 minutes. The second is 60% times, for Alex, he works at 25 minutes per application, and this is 15 minutes. And for Tina, since she has 2 jobs, the first one is for the homeowner's insurance. So 15 times 60% is her first job. The second, she also processes auto insurance. So we also have to account for that. So 20 times 40%. And this would equal 17 minutes. And then for Richard, he processes at 20 minutes. So 60% times 20, which equals 12 minutes. So that's the unit load. That's how fast they work, assuming that there's no wait time. And yes. So there's wait time in this case because 60% is the homeowner insurance and 40% is the auto insurance. So by multiplying it by the percentage, we're accounting for that wait time. So they actually work faster. So unit capacity is just asking for how many applications they can process per hour. So there's 1 hour equals 60 minutes. So the first one is just 60 minutes divided by the 9 minutes from here, which equals around 6.67 applications per hour. And then the second, so you divide all of them by the unit load. This one is 4 applications per hour. 60 divided by 17 is 3.53. And 60 divided by 12 is, I think, 5. And this is in applications per hour. Yes. Yeah, the 60%, right? The why we have to multiply the 60% here. Yeah, that part is tricky because what I said about the theoretical flow time is how an input flows from beginning to the end of the process, assuming there's no wait time. But since there's 60% of homeowner insurance here and 40% of auto insurance, not all of them is homeowner insurance, right? So they also have to wait for the process before the separation. Sorry, it doesn't show here. So you have to wait for the separation. So after they separate this, so this is accounting for basically all of these, how much they process an application in general. But if assuming that if they're all homeowners insurance, he would actually process faster than that because he wouldn't have to wait. Does that make sense? Okay. Yes. Both. Yeah, she's also processing the auto insurance as well as the. Yeah. Yes. So it's asking for the unit capacity rate. So the final answer is actually 3.53, right? The smallest. Yeah. So the final answer here, the bottleneck is the one, the stage that processes the least and it limits the capacity of the entire process, right? So in here, who is this? Tina only processes 3.53 applications per hour because she has to process both homeowner insurance as well as auto insurance. So this is the bottleneck, and the capacity of the entire process is 3.53. So that's D. So the bottleneck is Tina. Oh. Okay, and then for E, the manager of the insurance company believes that there is more demand to be served even though the firm is operating in capacity. And there are 2 options that were suggested. The first one is to shorten the time to do A3, so by 2 minutes. The second is to shorten the time to do A5 by 2 minutes. So what would you recommend? Okay, so if you shorten A3, so A3 initially took 15 minutes, and if you shorten it by 2 minutes, I'll take 13 minutes. So unit load then turns for Tina, unit load for Tina turns into 13 times 60% plus 20 times 40%, and this would equal 15.6. That's for A3. For A5, so A5 initially it is at sorry, A5. Okay, so A5 it was initially at 20 minutes, and if you shorten 2 minutes, it'll be 18 minutes. So the unit load for this would be 18 times, sorry, would be 15 times 60% plus 18 times 40%, and this would equal 13.2 minutes. So if you divide the first one, so this one will be the unit capacity here. So again, we're calculating in the same way. 60 over 15.6 would be 3.85 applications an hour. And here, 60 divided by 16.2 would be 3.7 applications per hour. And since 3.85 is bigger than 3.7, we can conclude that shortening A3 is better. Yeah, so shortening A3 will mean that they process more per hour. Yes, I'll just write it here. Yeah. Applications per hour. It's the same as what we calculated here, the unit capacity. So applications per hour. Okay. Does anyone still need this up? Move on. Okay, so the third question here. So a car maintenance at a loyal Toyota and body shop goes through either one of two parallel three-step processes and then merge into a single line for the final step. Capacities are shown on the diagram. Okay, so number one asks, what is the current capacity of the entire process? So again, this question emphasizes the bottleneck and the capacity calculations. So I'll just give you guys a minute to work on this question. Okay, so for this question, number one asks, what is the current capacity of the entire process? So what you need to notice here is that there are two parallel lines, so two different um, steps here, two different processes. So first, we need to find the bottleneck in each of these processes. Okay, so the bottleneck again is the point of congestion basically, and it is the step that produces the most and then limits the capacity of the entire process. So in steps 1, 2, 3 here, the bottleneck would be at 17. So 17, what is this producing? 17 cars per hour. And then 4, 5, in steps 4, 5, 6, I'll be at the 11 right here. Okay. So since they're happening at the same time, we add them, which equals 28 per hour, because if they weren't, like so for example, if you didn't look at this, and it was just 1, 2, 3, 7, 8, then you would just take the smallest, and that would be the capacity of the entire. Sorry, which one's 22? One and if they're not, sorry, I don't understand. For this part, was step 1, yeah? Yes, yes, you would. No, it doesn't matter. So say if this was like 20, like really high, like 30, so then this would be the bottleneck. So you would still add 1 and 5. So you would add the 20 and the 11, if that's the case. Okay, and then we have to compare, because for this section here, we know that it is 28 per hour. So we have to compare the 28 with the 38 as well as the 40, because they're the capacity of the processes that occurs afterwards. So we know that this is 28 per hour. So since 28 is smaller than 40 and 38, we know that therefore the bottleneck of the entire process is 28, the smallest capacity. Yeah. Because there's two parallel steps, right? So if you think about it, if something is happening here and something is happening here at the same time, so both the output here will be added. No, because this and this is independent of each other. Do you get what I mean? So if this is when 4, 5, 6 is happening, 1, 2, 3 is also happening at the same time. So say it's on a timeline, these two will be happening at the same time, and by the end, like say if the time is here, they would have produced the 17 plus the 11. Well, they have to finish here before it can get to 7, right? Yeah. Yeah. Yes. Oh yeah, I go. Yes. So it will be like the previous question. Yeah. Yeah. So if oh, okay. So because they're happening, so processes 1, 2, 3. So for example, if you're like making shirts and pants, right? So for example, 1, 2, 3 is for shirts, and 4, 5, 6 is for pants. So they can occur at the same time because they're independent processes. They're not using like the same factory or whatever. So by the time that you get to 7, when they're combined to form, I don't know, like, yeah, like a onesie or something, the pants and the shirt, we would have both of them. So you have 17 and 11. Okay. So this answers the second. So B. So we're at 28. The bottleneck of this portion is at 2, and the bottleneck of this portion is at 5. Okay, and then for C, if the logistics manager can increase the capacity of only one operation through process improvement efforts, which operation would he select? How much additional capacity would he strive for? And what would be the resulting capacity of the entire process? So the trick here is to target the bottleneck. Yes. Mm-hmm. Yeah. 7 and 8. Well, yes. So in this case, because they're combining into one step and they're evidently bigger, so I just compared the first view. Yeah. 7 was lower than this. So basically, you would take out the bottleneck for this step, bottleneck for here, and the bottleneck here, and you would compare the 3 of them. So if this one was lower than, say, the 17, then this would be the bottleneck. Yeah. Okay. So in this case, we want to increase the capacity of one of these processes, right? So if you look at steps 1, 2, 3, you can obviously want to increase the bottleneck because that one is the point of congestion. It limits the capacity of the entire process. So whenever it says whenever you can increase the capacity, you always want to increase the bottleneck. So the problem here is knowing how much can we increase. So we look at the next highest capacity here, which is at 20. So if you increase 17 to 20 per hour, if you increase it to more than 20, say it will be 21 per hour. For example, if you increase it by 4, then the bottleneck would still be the 20, right? Because it would be the lowest. So we realize that in this step here, no matter how much we increase, since we don't increase the 20 here, the new bottleneck would be the 20. So in this case, it would turn to 20 per hour. And then, so if we only change step 2, the capacity of the entire process would be the new 20 plus the 11 here, and it would be 31 per hour. And same with the second step. We can only increase it up to the second lowest or second highest step. So in this case, it would be the 12. So we can only increase it by 1, and 12 would be the bottleneck. So again, if say you increased it by 4, so it would turn into 15, the 12 would still be the bottleneck nonetheless. So in this case, it turns to 12 per hour. So there's 2 options here, 1, 2. And so if this one turned into 12 per hour, this one stayed the same. So it would be 17 plus 12, which equals 29 per hour. And when we compare these two, we obviously want the 31 cars per hour because it is faster. So therefore, the answer here would be increase capacity of operation from 17 per hour to 20 per hour. Okay, so that's the final question for the second part, which was the process analysis, so which is calculating the bottleneck as well as the capacities. So I'll just leave this up here. Does anyone still need this up? Okay, so the third question, the third section that he would probably test you on is multiple types and product process matrix. So that is basically distinguishing between these four different processes here. So the question I have for you is mark each of the following products on the appropriate positions on the product process matrix, and then briefly justify why you chose that. Okay, so I'll just briefly go over the processes here. So the first, we have job shop. Okay, so what the job shop is, some examples are, say, a hospital emergency room, customized like cabinets, for example. So basically, the key here is this word, customization. So the job process is different from the rest because it creates the flexibility needed to produce a variety of products or services in small quantities. So customization is relatively high and volume for any specific product is relatively low. So high, flexible. So they typically, what they do is they receive a customer's order and they don't produce ahead of that time. So as soon as they receive it, they would produce it. So that's why their volume is low and their variety is very high. The resources are organized around the process. Okay, and then next we have batch. So examples of batch are, for example, furniture manufacturing. So the difference here between the cabinets, customized cabinets here, and the furniture manufacturing here is these are customized. So if a customer says, I want my cabinet to look like whatever they designed, and this one is just general like IKEA furniture. So, and usually these are assembly lines because you would want, the quantities would be very large. Okay, so because of these large quantities, there's, unlike job shop, there's a narrow range of variety, so narrow range of products and services. And because this one is as soon as you get the customer order, that's when you start making it. But this one, there would be like some of the components would be produced in advance. So for example, in the case of furniture manufacturing, they would have like the wood ready to put into the furniture. And for assembly lines, they would have the parts of, say, if it's an assembly line for cars, they would have the parts ready. Okay, so again, large quantities, then job shop. So the next one we have flow shop. Okay, so examples would be producing appliances, computers, toys. So a lot of the things that we use, that we use daily. So again, the volume here is very high, and products and services. So if it's in, so these are obviously in the product sector, so they're products. If it would be in service sector, standardized would be as in like cafeteria food or like fast food restaurants. So the difference here is that the resources, so machines, are organized around the actual product or the service. Product. And orders are not directly linked to specific customers. So this basically means that, say a retailer or a wholesaler, they would order like in hundred thousands, and you wouldn't know whether, like, which specific person that product would be going to. So in this case, orders aren't on. Yeah, so there's little variability in products. Okay, and then the last one, we have continuous flow. Okay. So continuous flow would be high volume commodity products. So examples are like food items, chemical plants, so like plants making beer, plants making steel. And this is continuous flow is basically an extreme version of flow shop. So it makes extreme version of high volume standardized productions. Okay. So in this case, equipment is very specialized because labor is very specialized because they would just be making high volumes of the same thing every day. And it would be capital intensive to maximize utilization. Yeah, so it would be capital intensive because usually the process, as soon as the raw material goes in, it would just be processed without stopping through the entire facility, using the entire facility. So the entire facility is basically surrounded on that one type of product. So usually one primary material is used. Okay, so in this case, we have, so first of all, we have milk, and milk and cranberries are both food items. So like I said before, food items would go under continuous flow. So we know that it is in this area, and they are commodity products. So products we use every day, and they're produced in large amounts. There's not a lot of difference in them. So A and B would go under here. So for high-end cars, they are actually a special, so these cars, sorry, so C, E, and F. So these are actually at an extreme end of job shop, which is projects. So what projects are examples are construction, planning a major event, running a program, doing consulting work, for example. So these are basically a one-time thing tailored to one specific customer's needs. So these are high customization and low volume. So as low as maybe just one. So basically, they use a large scope of resources, but once the project is done, the resources are basically put to waste because it was just used for that one thing. Okay, so one-time unique items. So in this case, since there's not a lot of Rolls-Royce luxury cars, or McKinsey consulting projects is only tailored towards probably one company, one person. Sorry, not automobile assembly line. And as well as Boeing airplanes, it's just producing like 1, 2, 3 per year. So these would all go under job shop as one of a kind. So C, E, and F. Okay. Next, we have, so we'll look at batch. So for bakeries, for example, they wouldn't produce as much as flow shop. So flow shop will produce in thousands, tens of thousands. But for bakeries, maybe they will produce like 100 per day, and there would be some variety compared to, as say, in like flow shop. So bakery would go under low volume, but there's quite a bit of variety, and it would be batch. And finally, we have G, automobile assembly line. So as I said before, that would be batch. So like, for example, fixing automobiles, that would be flow shop. Yeah, so for example, fixing automobiles, the product and services are very standardized. When you produce automobiles like, say, Ford or like Toyota, it would be just one, the resources are all dedicated around that production process. So this would be G. Yes. Yes, it's an extreme version of job shop where it's only tailored towards like 1, 2 customers. Yeah. Yes, because job shop and like this is like related like this. Yeah, because I know he has a picture in his slides that looks like that, right? Where it goes like there's these things here and these things here, and then he has a line that goes down. Yeah, it's related to that one. Yeah. Mm-hmm. I can't really remember what, because I just looked over really quickly. It's just basically relating to these things here. We can look at it in the next question, which is, one sec. So the next question in this portion talks about differentiating job shop and flow shop in terms of these factors. So I think that's what he was pointing out, right? Okay, so differentiate flow shops and job shop in terms of, first of all, we have variable production cost. So variable production cost is basically variable cost, the cost to produce one unit of whatever they're producing. So flow shops, because they produce many units, they can reach economies of scale, and therefore they would have low variable cost. For job shop, because they produce in high variety and they dedicate specific resources to each of the units that they're producing, they would have high variable cost. Next, we have labor specialization. So for flow shop, labor would be highly specialized because they would, all the workers would just be engaging in the same activity, producing the same product over and over again every day. So high labor specialization. And for job shop, it would be low because there's highly skilled workers. Skilled workers. that produce different products. And another thing that he might ask is comparing them in terms of skill. So like I said here, job shop would have more skill. The workers there would have more skill than flow shop because they would be producing a variety of different items. Yes, like specialize in one single thing. Yeah. Okay. Third factor here, we have the size of facilities. So for flow shop, there's usually large plants dedicated to, again, that single product, whatever they're making in humongous amounts. And then job shop would have small facilities engaging in small independent projects. Okay. Next we have flow time. So again, how long do they take to turn an input into an output and get it to the customer? So for flow shop, since it is highly automated, so large plants and high labor specialization, this would mean shorter flow time. And for jobs, since it is very specific items, and there's less workers working on these different variety of items, this would take longer flow time. Okay, next we have volume. So job shop would obviously produce in small quantities, and flow shop would be large scale mass production of a particular product. Okay. Then we have product variety. Okay, so for product variety, due to the specialization of labor and producing products in small quantities, so job shop have the capability of producing a large variety. And well, flow shop would be the opposite. And the next important concept here is work in process inventory. So for flow shop, because there is shorter flow time and cycle time, so it would have lower work in process than job shop. So work in process is just the amount that's currently being produced. They're not finished goods yet. Okay, and then we have the automation as well as the capital investment. So these are basically the same category. If there's highly automated, it would have a large capital investment invested into it. And so since job cost uses general purpose equipment due to the fact that a lot of it is basically the skilled labor, so general purpose equipment, while flow shop would be expensive specialized equipment due to the fact that, again, it produces a large number of the same product. So for job shop, it would be low capital investment, low automation, And for flow shop, it would be high automation and high capital investments. Okay, so that concludes the first 65% of the review session. So we can take a 5-minute break. So it would be great if you guys can fill out the survey for my teaching. And do you know it's online, right? Yeah. So it'd be great if you guys can fill that out during the 5-10 minute break that we're gonna take right now. And there's a chance to win a $10 Starbucks gift card if you guys participate. Thank you. Yeah, sure.
Just a batch continuing some accounting.
Yeah.
And so you'll have like batch costs, which is where you have, like, for example, milk. If you're making milk, and milk is throw it all together at some point, you pasteurize it all at the same time. That would be a batch. It's not the same thing, right? Because I'm assuming it's like the level of standardization.
I think in this case we would classify, like, are you mixing it with the
Just as if a lot of processes have
like process cost versus job cost, right?
Yeah, it could be.
That's why you guys
Yeah, I guess that would make sense.
So in accounting, they would use that general like process cost for all commodities that you would make in like 100,000.
Yeah.
Right? But in this case, we classify, so flow shop would be in even bigger quantities than batch.
Okay.
Yeah. So batch, I use the bakery example, right? So maybe they would produce 100 pieces of bread a day. But if it was milk and they were selling it to like stores, retailers, it would be in like thousands.
Okay.
Yeah.
Sure. Cool.
Okay, so I'm going to get started with the fourth section. There's only variability in processes and then project management left. So we're going to start with the true and false question. So according to Little's law, the inventory equals the product of the throughput rate and the flow rate. The key here is the at any time. So is that true or false? So this question is actually false. And it's actually very tricky because Little's law is for long run averages. So in this short run scenario, the Little law is inventory equals the throughput rate times the throughput rate times the average time at the server. So this does not necessarily hold. And again, I said the key here is the at any time. So for example, say like a bank opens at 9 a.m., but there are some customers who are already waiting outside at 9 a.m. before it even opened. So in these cases, these customers have already arrived and they're waiting outside. Then we assume that the throughput rate, so this rate here, would equal 0 because they have not actually gone through the process, so they have not, so the throughput rate is 0. Nothing is happening because they're just waiting there outside. The bank has not opened. And then, so when this is 0, just math concept, this would be 0 as well. So anything that multiplies by 0 equals 0. So here we would think that the inventory is also 0. But this is actually not the case in this case because the customers are waiting. So this would actually not equal 0 since people are already waiting outside. So this is a tricky question. I don't think it'll be this tricky on the exam. The trick here is just to look at the keyword at any time. Okay, so now we're going to go through the queuing system, the 4 different types of systems and the complicated formulas that he would give you. So I'll go through them first. Okay, so I know that he started teaching, he began with the PK formula. Hope this sounds familiar. So the PK formula, so that was what was given. So the important here to recognize when to use the PK formula is that it assumes that there's a single server, single lineup, and an infinite source. So an infinite number of customers can come to wherever the store, for example. And the key here is that the arrival rate and the service rate follow a general probability distribution. And he calls it the GG1 formula. And this is assuming it's following a general probability distribution because you're assuming that you know the arrival rate and the service rate of people who's coming. So you know that, oh, this customer will come every 5 minutes or so on. So you can actually graph it because you know all these points. But what if we don't know all these points? So what if we don't have any data about the processes? So that's when there's 3 different types of other lines that he went over. So obviously in this case, the simplest arrival process is when there's completely regular arrival. So again, it would be this PK formula because you would know when they're going to arrive, but this is very unrealistic in real life, right? So realistically, you would not know when the next customer is going to come to the store or how fast they're going to be served. So when this is the case, there is an exponential distribution. So do not know or have data on arrival and service rates. So again, I'll just stress that here is the general probability distribution, and this is an exponential distribution. And this is because we do have the data on the customers, but this one is we do not. And again, we use exponential distribution because it makes it very easy for us since the coefficient of variation here for the arrival time as well as the service time, they both would equal 1. So there's 3 types. The first one would be single channel, single server, infinite source, and exponential for both. So exponential for service rate and arrival rate. An example of this would be a one-person barber shop, for example. And he calls it the MM1 lineup. So in this case, the average size of the line would be this formula here, and this is just given from him. The average size of the entire system. So this includes the people who are being served at the moment, not just the people in the line. So this would be so again, this means the average input rate, and this is the processing rate. This the mean. Okay. And so again, for this first type here, the average time spent, so the average time that you would spend in the queuing the line would be with the Little's law, according to the Little's law, would be that formula there. So that summarizes the first type. So again, it's a single channel, single server, exponential service times. So second, we have also single channel, single server. But what is the difference between the second and the first one is that the service pattern, the service rate is constant, and the arrival rate would be exponential. So unlike this one, both is exponential. This one is constant, one is exponential. So again, an example of this would be a roller coaster ride. So the people who want to go on the ride would arrive at different rates, but the number of people served would be the same because the roller coaster would go around at the same time, at similar time intervals. And he calls this the MD1. So this one is MM1. This one is MD1. Okay. So here, the average size of the line, is calculated by and if you want to know why this one is half of the first one, it's because, so in the first one, we assume that the coefficient of a variation for both, because it is a exponential distribution, these are both equal 1. So this will be just 1 plus 1 equals 2. 2 divided by 2 is 1. So the first one is just, we just didn't show it because that would just be 1. So it would just be this formula here. But in the second example, since the service rate is constant, the coefficient of variation, which means how much there's deviation from the mean, it would just be 0 because it would be at a constant rate. So therefore, if one of this is 0, the other is still exponentially distributed. So it would be 1 over 2. So 1 plus 0 equals 1. 1 divided by 2 is 2. So that's why we have a times half here. Okay. So in this case, the average size of the system would be IS equals IQ plus and the average time in the line would be the same. It would always be using the Little's law, so it would be same as this one here. Okay, so the third system that we have is a multi-channel system. This one is the most complicated. And so this one, again, infinite source population. It would be one line, multiple servers. And exponential arrival and service rates. So an example of this would be the tellers in a bank. And he calls this the MMC, with C symbolizing the number of servers. So in this case, the average size of the line, so how many people in line, would be with this formula. So it's to the power of, and again, since it's exponential, we disregard the variation formula here, because it would be 1 plus 1 over 2 again, and that would just cancel out. Okay. And I also want to note that if it asks you for the probability of, say, what's the probability of when a person enters the store, they'll find 3 or more people in line. So the probability of whatever it is in person in line is given by this formula, with n being equal to the number of units in the system at that moment. Okay, so that sums it up. Okay, so now we have the question here. At the Canadian-USA border, vehicles arrive at a rate of 10 per minute, assuming that there's only one lane and one inspector who can inspect vehicles at a rate of 12 per minute in an exponentially distributed fashion. So if you look back at the 4 different types, the 3 different types, as well as the PK formula, we would realize that this falls under the first type. So this would be the MM1. Okay, so this is the MM1 system. The arrival rate is 10 vehicles per minute, and the service rate is 12 vehicles per minute. So it's very efficient to just label everything here so you know later on when you use them in the formula which numbers to use. So A is asking what would be the average length of the waiting line. So if you look back at the formulas I gave you for the first type, IQ equals over. So with that being said, you just put the numbers in. Sorry, 12 minus 10. And you would get 4.7 vehicles. So the average length of the waiting line would be 4.17 vehicles in line. Second, we have what would be the average time that a vehicle must wait to get through the system. So, so this includes the time being served at the actual station. So again, we would use the formulas I gave you. This one is for the average size of the system. And it would equal 10 over 12 minus 10. So this would equal 5 vehicles. So this is the number of vehicles in the system. But the question here is asking, what is the time? So we need to use Little's law. So Little's law. And we can just plug the 5 in. The arrival rate is 10. So we would get 0.5 minutes. So for C, what is the utilization of the inspector? So utilization is the P in this case, and it is just the arrival rate divided by the service rate. So 10 over 12 equals 83.33%, and you would always express it as a percentage. Lastly, we have what is the probability that, say, a car enters the system, goes in line, what's the probability that when you arrive there, there's 3 or more vehicles ahead of you? So 3 or more. So the probability that, say x is equal to the number of cars in the system currently, so the probability that there's more 3 or more vehicles ahead of you would be equal to 1 minus the probability that there's 1 vehicle ahead of you, plus the probability that there's 2 vehicles ahead of you, plus the probability that there's no vehicles ahead of you. So remember the formula that I gave you? It was probability Pn equals 1 minus probability. Okay, so we can calculate the probability that there's 1 vehicle ahead of you. So P1, and that would just equal 10 over 12. You're just plugging the numbers in. So n equals 1 and to the power of 1. And that would equal 0.1389. So next, you have n equals 2, so 2 vehicles, x equals 2, which equals 1 minus 10 over 12, 10 over 12 to the power of 2, which would equal 0.1157. And next, you have the probability that there's no cars ahead of you, n equals 0. 1 minus 10 over 12, 10 over 12 to the power of 0, which would just cancel out, it would equal 1. And this would just equal 0.1667. So the probability that there's 3 or more cars ahead of you would be 1 minus 0.1389 minus 0.1157 minus 0.1667, and it would equal 0.5787. So if the question was worded as, what is the probability that there's more than 3 cars? So not just 3 or more cars, like there's more than 3. So you would also include the probability that there's 3 cars ahead of you. So Px equals 3, and you would subtract that from the entire, from this equation here. Okay. Do you still need this? Yeah. Yes. N equals 3. No, if you when you calculate n equals 3, it's if the condition is that there is more than 3 cars ahead of you. So you do not, it does not equal 3. So right now it's will be 3 or more, right? So the next question is, you're a customer service manager at TD doing logistics planning. There are 6 tellers working in the bank. Tellers take 15 minutes per customer with a standard deviation of 5 minutes. On average, one customer arrived in every 3 minutes according to an exponential distribution. So how many customers will be waiting in line? Okay, so you notice here that this one is the third type. It would be the MMC with the multi-servers, multi-channel. So this is question 3. Okay, so we need to do that, we need to find out using the formula, and notice here that only the arrival rate is exponentially distributed. So we do need to calculate the coefficient of variation for the service rate. Okay, so remember that the PK formula, 2 plus 1. Okay, so since the arrival rate is exponentially distributed, we know that CA equals 1. And the coefficient of variation, the formula, coefficient of variation, the formula is just the standard deviation over the mean. So for the coefficient of variation for the service rate, it would be 5 over 15, which equals 0.33. And C is the number of units, right? So C, number of servers, would just be 6, because there's 6 number of servers. And the tricky part here is the arrival rate and the service rate are always expressed as customers per time unit. So we never express it as, time unit per customer. So in this case, it's very tricky because they give you the time unit per customer and you need to convert it to customer per time unit. So what you do is 60, so 60 minutes in an hour divided by 3, divided by 3 would equal 20 customers per hour. And the second will be 60 divided by 15, the rate, and it will be 4 customers per hour. So the utilization here would be 20 over 6 times 4, and it would be 83%. So now that we have everything that we need to use in this formula, we would just plug it into here. So equals 0.83 to the power of 2. There's 6 plus 1 over 1 minus 0.83 times 1 squared plus 0.33 squared over 2. And this would equal 1.62. Okay, so this is the answer for A. For B, the question is asking, on average, how long would a customer spend in the bank? So you would need to figure out, okay, so the total time in the bank would include the time in the line as well as the time in the system. So it would equal time in the line plus TS, so in the line in the system. And this is calculated by plus 1 over. This is just given from the PK formula. And if you plug this in, 1.62 over 20 plus 1 over, plus 1 over 4. Yeah. And it would give you 0.334 hour. So in this section, it's just applying, figuring out what these variables are and just applying them to the formula. So it's really, we need to stress on which line model to use. So that should be something that you guys focus on when you're studying. Okay, so the last section would be project management. So the question is, say you're given the data here for an activity, for a project, and you want to calculate what is the critical path. So the critical path is the length of the longest path through the system. So first, for A, you will always draw a network diagram just to make it easier for yourself to see it in a visual way. So first we have activity A takes 4 weeks. So activity A precedes B. So you know that B would be afterwards, and it took 3 weeks. C is also preceded by A, and it takes 2 weeks. Then you have D, which is just preceded by B. So D takes 5 weeks. And E is preceded by B and C. That goes into E, and it only takes 1 week. F is just preceded by C, and it takes 3 weeks. G is preceded by E and F, and it takes 4 weeks. H is preceded by D and E, taking 4 weeks as well. And then finally we have I preceded by H and G, and it takes 6 weeks. So that's just the diagram for this path. Okay, so how do we know which one is the critical path? So what you do is you can list all the possibilities from A to I. So for example, there are actually 6 paths through this diagram. First one is A, B, D, H, I. So you can go this way, A, B, D, H, I. You can go A, B, E, H, I, A, B, E, H, I. You can also go A, B, E, G, I, A, B, E, G, I. And you can also go A, C, E, H, I. So A, C, E, H, I. A, C, E, G, I would work. A, C, E, G, I. And A, C, F, G, I. So A, C, F, G, I. So how long does it take for each of these paths? How long do these paths, the duration? So for first one would be A takes 4 plus B takes 3, D takes 5 plus 4 plus 6. So you're just calculating the length of this path. It would equal 22. The second one, 4 plus B is 3 plus E is 1 plus H is 4 plus I is 6 equals 18, and so on. 4 plus 6 is 18 as well. 4 plus 2 plus 1 plus 6. Okay, so now that you know how the duration of all of these paths, you want to know which one is the critical one. So the critical one is, as I said before, the longest path through the process. So we know in this case 22 is bigger than the rest. So the critical path would be A, B, D, H, I. And therefore, the estimated completion time for B would just be the 22 weeks. Okay, and the last question we have for tonight is, to shorten the project by 3 weeks, which task would be shortened, and what would the final total project cost be? Okay, so crashing is definitely going to be part of the exam. Here. So crashing means reducing the duration time of an activity. And note here that if you reduce the time of an activity on a critical path, it may change critical path. Critical paths may change. Okay, so right now in the chart, we have the normal time. I'll just label it NT, the crash time, CT, the normal cost, NC, and the crash cost, CC. So to calculate the crash cost per time period, the formula is just CC minus NC over NT minus CT. So for example, for activity A, we have that CC equals 11,000, NC equals 10,000, NT equals 4, and CT equals 2. So we would get 1,000 over 2, which equals 500 for activity A. And we know that in this case, the possible decrease would just be the NT minus the CT, which equals 4 minus 2 equals 2. So you do need to calculate the crash cost per time period as well as the possible decrease for every single activity in the project. So A, B, C, D, E, F, G, and I. So we know that A cost to crash per week and the possible decrease. So it would be 500 and this would be 2. So I'll just give you the rest. It's just using the same formula. You can calculate at home. 1, 2. Sorry, H. Okay, so we know that in this case we want to, the question asks to crash 3 weeks of the project. So first we would look at the critical path, which is the longest. So we always want to choose the cost, the activity that costs the least. So in this case, out of all of these costs, it would be activity A. So step activity A by 1 week, and this would cost $500. And you realize that activity A, the cheapest, there's two possible decreases. So step 2, you can actually crash it again. And this is also same thing, $500. For step 3, the last week that you can crash, you realize that A is no longer available. You have used up the full 2 possible decreases, so you have to crash something else. And you look at the next highest, so the next lowest cost. So you look at B, D, H, and I, because these are the ones on the critical path. Remember, the critical path is A, B, D, H, I. And you look at which one is the lowest. So the lowest here would be the 2000, activity B. So the third step here would be to crash D at $2,000. Crashing method. So to calculate the total cost of the entire project after the crashing, you want to sum the entire normal cost for all activities. So that's the everything here. So I think that equals 94,000. And then you would add the crash costs incurred. So that's the 500 plus another 500 plus the 2,000 over here. So you would get 97,000 as your final total cost of the project if you crash 3 weeks. Any questions? Okay, yeah. Yes, because the critical path is the longest path in the project, right? So you will always want to shorten it. Like it's the path that determines how long the entire project would be. So you always want to crash something in the critical path. But for example, if this one was really low, like say 19, and changing this would change another path, and that path becomes critical. Yeah, so you would have to change everything. So say we crash, because for example, when we crash activity A is part of all of these things. So actually all of these, when we crash activity A, they all get reduced. So this gets into 17, 16, and so on. So you would have to do that for every single path to determine if the critical path has changed. To the new critical path. Lowest cost. Yes, because you're always crashing the lowest cost, right? Yes. You always choose the lowest cost first, and then you look at that. Yes. Yeah. Okay, thank you. So for whoever didn't do the survey yet, it'd be great if you can do the evaluation for me. Thank you. for when you have to add both of them, so for the entire system.
So
And you can calculate them